based on tacticity, and I'll be discussing with you, before we discuss classification, what do we mean by tacticity, and then classification based on molecular forces. So to begin with this classification, let's understand what do we mean by the term tacticity. Tacticity is defined as the way pendant groups means the side groups or the functional groups are arranged along the backbone chain of a polymer. In the polymeric structure, the main backbone chain is constituted by an organic group, and the side groups, generally the functional groups, are arranged in various manner. So depending upon the arrangement of these functional groups along the backbone chain of the polymer, that is the organic backbone chain of the polymer, these polymers attain different atomic configurations for the same composition. So based on the orientation of the side groups, these polymers can be classified as isotactic polymers, syndiotactic polymers, or atactic polymers. The properties of these polymers are highly dependent or are majorly affected by how these side groups are arranged along the backbone chain, that is tacticity, greatly affects the properties of the polymers. To understand this tacticity, I'll be taking up the example of PVC, that is polyvinyl chloride. First, to take up, what are isotactic polymers? Isotactic polymers are the polymers in which all the side groups, that is functional groups, in the case of PVC, we'll be mentioning it as chlorine, are arranged on the same side of main chain. These are called isotactic polymers. As you can see here, all the chlorine atoms are arranged on the same side. This is the functional group, this is the main backbone chain, and the Cl atoms are arranged on the same side. If we see the wedge and hash notations in the atomic configurations, all the R groups, that is the chlorine atoms, are on the wedge bonds. Here also it is on the wedge bond. Here also it is on the wedge bond, then on the wedge bond again. So they are pointing towards the same side. These are isotactic polymers. Whereas in the case of syndiotactic polymers, these are polymers in which all the side groups are arranged in alternating fashion around the main chain. What do we mean by this? In this atomic configuration, that is in the wedge hash model or notations, you can see this R group, that is the chlorine atom, they are once on the wedge bond, then on the dash bond, then wedge bond, then again dash bond, that is in the alternating manner. Once it points away from us and the other it points towards us. So these are syndiotactic polymers. In the case of atactic polymers, there is no fixed arrangement. There is no fixed order, neither on the same side, neither in the alternating manner. Rather, the side groups are arranged randomly on the main chain. As we can see here in this model, again, this is wedge and hash dash model, and I am taking up example of PVC. This R group, that is chlorine atom, is on the wedge bond, then again on the wedge bond, then dash, then again wedge. So there is no fixed order. So as we observed in the case of isotactic and syndiotactic polymers, there was a fixed order either on the same side or on the alternating fashion. So these isotactic and syndiotactic forms are stereoregular structures. That is, they follow a certain symmetry. Since they follow a certain symmetry, these isotactic and syndiotactic polymers these chains can get closer to each other, resulting in some intermolecular interactions. Since they can interact, they have strong tendencies to crystallize. That is, they occur in crystalline form. They have good strength. While in the atactic forms, these are amorphous because these atactic forms do not follow a certain order. and hence they do not have crystallinity in them. That is, they are amorphous in nature. A very important polymer, that is Kevlar. They are a Kevlar, polypropylene. Kevlar is popularly used to make bulletproof jackets. It has high strength. These are the examples of syntactic polymers. Polypropylene, if it is in atactic form, it is gummy solid, while isotactic version is highly crystalline and tough. So, depending upon which form of polymer is being synthesized using various catalysts and special techniques, it depends that which form it will take up. It will take up in the form of it will be synthesized as atactic polymer or syntactic or isotactic. So, and in the case of, if I discuss the example of atactic polymers, we have already seen that they are amorphous in nature. Example being PMMA, polycarbonate, polymethyl methacrylate. So these are the certain examples of atactic polymers also. And next is classification based on molecular forces. If I take up classification based on molecular forces, it can be categorized as elastomers, fibers, thermoplastics, and thermosetting plastics. So firstly, I'll be taking up elastomers and fibers. Elastomers are the polymers that are held together by weakest intermolecular forces. That is, they have elastic behavior. The intermolecular forces between the various chains are weakest. They can be stretched 3 times to their original length, but again return to their original shape and dimension as soon as the stretching force is removed. So the example is natural rubber. And coming to fibers, we are already familiar with the fibers that we use, that is polyester, silk, nylon 66. In these, the polymeric chains are held together by strong intermolecular forces like hydrogen bonds or dipole-dipole interactions. Since they are held together by strong intermolecular forces, that is, the polymeric chains are interlinked via strong bonds. They are crystalline in nature and have high tensile strength. Next, in the category of molecular forces, very majorly, we'll be discussing thermoplastics and thermosetting plastics. Thermoplastics are linear, long chain polymers. They are generally formed by addition polymerization reaction. Addition polymerization reaction I had already discussed in the previous lecture when we discussed the classification based on polymerization mechanism. In that, we discussed that they are linear long chain polymers. Since they are linear and the one chain cannot very well interact with the other chain via strong bonds, they get softened on heating. That is, one layer can move over the another layer very easily. That is, they can creep. So this allows for molding. Molding means they can be reheated and cooled again. And by doing so, we can say that they can be recycled. They can be remolded and they can be recycled. And in doing so, the chemical and mechanical properties of the polymers do not change. There is no cross-linking between the polymeric chains, as the polymeric chains are held together by weak van der Waals forces. And this is the reason that they get softened on heating and they can be molded and can be used again and again. Examples of thermoplastics are very common, that is polyethylene, polyvinyl chloride, whose uses are very, very obvious, and Teflon. Teflon is used as a coating in non-stick cookware that we use in our households very importantly. And this PMMA, that is polymethyl methacrylate, this is also known as, or this is popularly known as acrylic glass. This is used as an alternative to glass these days because this is lightweight and shatter resistant. So this is a very important thermoplastic used these days as a substitute for glass. Now, the major advantage of these thermoplastics is that they have very good shelf life. For example, I purchase a monomer someday, but I plan to polymerize it later on. So we can easily handle that in the case of a thermoplastic. Now coming to thermosetting plastics. These are strong and hard polymers as they are formed by condensation polymerization reaction. Now what is condensation polymerization reaction has already been discussed in the second lecture of the series. In this, the polymeric chains, the individual polymeric chains in the thermosetting plastics are linked to each others via strong covalent bonds. That is, there are cross linkages amongst the polymeric chains. So they do not soften on heating. Hence, once molded, they cannot be reshaped. That is, they set permanently. So they cannot be recycled or reused. Now, the major disadvantage of this is that they have very less shelf life. No doubt, if they have a limited shelf life, but they have excellent thermal and chemical stability once the polymerization takes place. For example, if I buy a super glue from the market and if I forget to close it, and when it comes in contact with the air, the polymerization takes place and it gets hardened and that glue is useless for you. So they are permanently set and it gets useless. In the examples of thermosetting plastics, we have bakelite that is very well used in phones and other materials, and polyurethane is a very common example. This is the foam we use in sofas that is popularly known as PU foam. And the other is melamine formaldehyde that is used also in various household appliances. Bakelite is used in making dryers also. So these are the certain examples and applications. And how do we differentiate thermoplastics from thermosetting plastics? In the next session, I'll be taking up with you, that is in the fourth lecture of the series, I'll be taking up with you molecular weight of polymers, degree of polymerization, and variation of mechanical properties of polymers with degree of polymerization. Thank you.